Good morning, Honors Physics students, and welcome to another episode of Honors Physics. It's Mr. Finn again, trying to reach you guys today, the Tuesday after break. I'm hoping you guys had a great day yesterday and your first day back, and hopefully you're staying healthy and happy at home, sheltering in place for the COVID-19 outbreak, worldwide pandemic. Anyway, guys, just touching base a few things today. Yesterday we had our lesson on polarization and friction as a way to create charge on an object. So today, what I wanted to do is show you a secondary way, because I did have a couple questions from people saying, well, friction is a way to charge. Are there other ways to charge an object other than friction? Of course, the answer is yes, and we've got to figure out what those ways are. But in addition, I also wanted to revisit that polarization concept in another vein. So let's look at the electroscope. What is an electroscope? Well, an electroscope is simply something that shows the presence of charge. So if you can see here, it's just a plastic base with a little plastic kind of a stem here. And on that plastic stem is bolted a large plastic ring. So it's plastic on the bottom, plastic here, plastic here. Inside of that plastic ring is a rod, metal rod. Now it stems from this ball up top. So metal ball down through here. You can see it goes through there. Kind of bolts here. And then it's like a skinny S-shaped frame. And on that skinny S-shaped frame is a bar. You can see if I just click that bar just a second. It's a very lightweight bar, but the bar is hinged right above its center of mass. So that if I do disturb it, kick it out a little bit, and I hold on to that, the bar will eventually come to rest in an upright position. Well, that makes sense, because if I held this thing above its center of mass and I just displace it a little bit, it will come to rest where the center of mass is below the point where I am hinging this object. Just like a picture. If you can kind of center a picture on the wall, it should center at the spot where the center of mass is right below the nail or the hold area. So this electroscope will be in a rest position when this bar is vertical. Okay? You guys got that? Okay, so let's go to, I'm just going to reverse the camera around so you can see me playing around with this. I'm going to be using just my fur, my rubber rod. Now remember, guys, this is a rubber rod. Actually, I don't think I've shown this before. This is a rubber rod. And you can see that it's kind of hard, doesn't bend very much, but it is made of rubber. But it's just a hard rubber. And rubber is an insulator. Hair is an insulator. Fur is an insulator. But metal is a conductor. So what is the difference between conductors and insulators? Well, that's actually pretty basic. Conductors have a lattice structure which allows the electrons to move freely amongst the lattice structure. So electrons can fly freely around in a conductor, whereas in an insulator, electrons are tightly bound in place. Now this isn't to say that they're not moving. That would be physically impossible. Actually, it's a limit. It's called absolute zero. But electrons don't ever stop moving. They just jiggle in place, but they're not allowed to go very far from where you've deposited them. That is why when we deposited, let me see if I can grab my balloon here for a second. That is why when we deposit hair on this balloon, the charged electrons that are deposited on this balloon are actually confined to the area where we deposited them. They're not able to move all over the balloon wherever they want. So when I rub the balloon with the fur, wherever I actually used that rubbing, that friction, that is where those electrons will be, in an insulator instead of a conductor. So insulators, electrons tightly bound in place. Conductors, electrons free to move all over the place. So that's a big, big part of what we're about to do. All right, so let's take a look at this electroscope and find another way to work. Okay guys, now I've got my electroscope set up on the table here. I've got my rubber rod and I've got my fur. So what I'm going to do is I'm going to use the fur to charge up the rubber rod. I'm just going to use some friction and I've charged up the rubber rod. Now as I bring it close to the electroscope, gently touch the electroscope. Well, I almost touched it, didn't quite touch it. So I get close, but do not touch the electroscope. You can see that the electroscope arm deflects. So I'm close, did not touch. Okay guys, so let's review real fast. Charge up the rubber rod, bring it close to the electroscope. Now why does the needle deflect? Why does the needle deflect in the presence of this charged rubber rod? Let's have a little think about that question. Okay guys, let's check out what's going on here. On the left, I just have my electroscope with nothing near it. Now obviously I didn't draw in the positives and negatives, but safe to assume that this metal ball would have positive and negative charges of equal quantity all the way throughout its frame and throughout the bar as well. But with no charge nearby, nothing's really happening. The one on the right has a ball that has a charge near it on the right. So I brought my rubber rod in with negative charge on the right-hand side. Now what does that negative charge do? It polarizes the electroscope. So I got my negative charges that are in the ball, and because they're free to move, because the ball is metal and it's a conductor, those electrons run down into the bar and occupy a position on this bar because they're trying to get away from other like charges. Remember from yesterday, like charges repel and opposite charges attract. So if I have a large negative charge here close to this ball, and electrons are free to move within the ball, then those electrons will run down inside the scope. When I remove the presence of this negative charge, the scope will go back to its regularly distributed system where electrons and protons simply run back to their neutral position. Now, what would happen if I actually touched the electroscope with the bar, with the charged rubber rod? Let's take a look and see what happens. Okay guys, here I am with my neutral electroscope again. I'm going to charge up the rubber rod, and all I'm going to do is just touch it real quick. Now if I touch it, hopefully you can see that the bar does not return to its neutral position. The bar remains deflected. So something about this bar touching that ball made the bar deflect, and it simply won't go back to its other position. It's now showing the presence of charge. If I put a little bit more charge on this rubber rod and bring it close, the bar deflects even more than it was a moment ago. That is very interesting. So what happened to the electroscope when we touched it with the rubber rod? This time we have something called conduction going on. Conduction is by contact, charging by contact, which means when I touched the scope with this rubber rod, charge was able to move from the edge of this rod onto the ball. And because it went onto the ball, those charges are able to spread out wherever they want because the metal is a conductor. Now, as you can see, I still actually have can actually pick the scope up and show you that the needle is deflected. Now I'm just holding the bottom. Remember, I'm holding the insulated portion, not the conductive portion. So those electrons cannot move off of that scope because they can't move into an insulator, but they can move throughout the conductor area. Now, by electron repulsion, they would want to assume spots on the bar. So what we have here is electron repulsion energy between the frame and the bar. Electrons are repelling themselves, trying to find places far and far away from other electrons. And the best possible case for them to do that is by making the bar deflect. Now you may be asking yourself, Mr. Finn, how long will that last? Charging by contact. Well, it depends. Depends on the area and depends on the weather. The weather. Yeah, because if there's a lot of moisture in the air, eventually we're going to lose or gain electrons due to the moisture in the air. But a better way to do it is to simply touch it. Touch this thing, and I'm going to ground the whole system. Hey, isn't that dangerous? Could I get shocked? Well, if you had a lot of charge involved, you would. But let's see if I touch it, if I get shocked. Now, if I stop breathing or something, if I go over in this chair, somebody's going to call 911 and get somebody over here. No, I'm just kidding. I actually didn't feel anything. I grounded this scope. So by me touching the scope ball, I'm allowing electrons to move up in through the frame and into me. I represent an infinite reservoir of neutral charge for the scope. That's called ground. A ground definition is an infinite reservoir of neutral charge. Well, that's it, guys. So simply, charge by contact, called conduction. The introduction of the electroscope as a way of measuring charge. And obviously charging by friction and polarization occur today too. Tomorrow we'll look at induction, maybe a way of just quantifying how much charge and how much force is available by a thing called Coulomb's law. Now remember, guys, Thursday I'll have a short Google form ready for you, and we'll try to have a Google form ready for every week so you guys can have some opportunities to put some scores together. Other than that, have a great day, guys, and we'll see you tomorrow.